Albert and Arthur each won a Nobel Prize for describing what every radiologic technologist should know about X-rays. My name is Lazar Lazarovsky. I've been a radiologic technologist since 2005. I'm the host of the Radical Life podcast and the creator of the 21-Day Registry Review Challenge, a highly structured course that follows the ARRT specifications outline, is taught by over 40 instructors, and helps students reduce overwhelm, erase anxiety, and pass their registry exam with confidence. Today, we're going to be talking about photon interactions with matter, the kind of interactions that occur when X-ray interacts with a patient's anatomy at an atomic level. As always, all of the concepts that you need to know are included in the description below this video, along with a link to a registry-style exam that's based on everything we'll be discussing today. With that said, there are three types of photon interactions that can happen with matter. The X-ray can be transmitted, that is, it can pass directly through the patient's body and hit the image receptor. Second, it can be attenuated or absorbed by the patient. And lastly, it can be scattered. We begin our discussion with the photoelectric effect, often called photoelectric absorption or attenuation. Back in 1921, it won this man right here the Nobel Prize in Physics, and it's still relevant for us today as radiologic technologists, as we'll see in a moment. Let's start by defining what it is, and then we'll break it down by looking at a diagram. The photoelectric effect is an interaction in which an incident X-ray photon transfers all of its energy to a tightly bound inner K-shell electron, ejecting it from the atom as a photoelectron while completely absorbing the X-ray photon. Now let's break down what that actually means. The X-ray photon, either Bremsstrahlung or K-characteristic, enters the patient, finds an atom, and transferred all of its energy to an inner shell electron. The X-ray itself then ceases to exist at this point. All of its energy now belongs to that inner shell electron. If that transferred energy exceeds the electron's binding energy, meaning how tightly it can hold an electron in that spot, the electron is ejected from the atom. This ejected electron is called a photoelectron. If we wanted to determine what energy the electron has, we would use this formula. The energy of the photoelectron is equal to the incident energy of our X-ray beam, our X-ray minus the energy required to release that electron, the binding energy of that electron. So this photoelectron has the energy of this incident X-ray minus the binding energy of the electron it interacts with. Now, once that inner shell electron is removed, the atom becomes unstable because there is now an empty space or vacancy in the inner shell. As we've seen in the lesson on target interactions, this creates instability within the atom. To fix that problem, an outer shell electron drops down from a higher energy state to a lower energy state to fill the vacancy. When that happens, energy is lost, and that loss of energy is released as a characteristic X-ray. So you may be wondering, doesn't this characteristic X-ray then go off and make contact with our detector? And that would be a valid thought, but there is a reason this characteristic X-ray will never reach our detector. When we look at characteristic X-ray production, our target material that the electrons interacted with was tungsten. It had a high atomic number of 74. When we're dealing with X-rays interacting with matter within a patient, our average atomic number is only around 7. The binding energies here are much lower within the patient's tissue as opposed to the anode target material. So the energy of this characteristic X-ray is very small, less than 1 keV, and that X-ray will therefore be totally absorbed within the patient's tissues. It just does not have enough energy to exit the patient, even though it is being produced during this interaction. So again, the main idea is simple. Photon in, electron out. The original incident X-ray photon is completely absorbed. Outer shell fills the vacancy of the inner shell. It loses energy. That loss of energy gets converted into a characteristic X-ray. That is then absorbed within the patient's body. Why? Because it interacted with an atom that had a very low atomic number and therefore not enough energy to exit the body. Now, let's talk about why this matters clinically. First, the photoelectric effect increases patient dose. And the reason is all of that X-ray photon energy is deposited into the patient's tissue. The photoelectron that gets ejected can go on to interact with nearby atoms and tissues, which contributes to ionization. So from a radiation protection standpoint, photoelectric absorption is not something we want to increase unnecessarily because it means more energy is being absorbed by the patient. But here's the good news for us. Photoelectric absorption does not create scatter radiation. Since the X-ray photon is completely absorbed, there is no scatter photon flying out of the patient toward the technologist. So when we talk about occupational dose or dose to the radiologic technologist, the photoelectric effect does not add to that exposure rate.
Yay!
Now, there's even more good news for us. It has a very positive effect on the way our X-ray image comes out.
Man, this just keeps getting better and better.
The photoelectric effect is one of the main reasons we have image contrast. Think about a chest X-ray, for example. Air in the lungs does not absorb very much radiation, so more photons pass through and reach the image receptor. That area appears very dark. Bone, on the other hand, absorbs more radiation because it has a higher atomic number and greater density compared with soft tissue. Since fewer photons reach the image receptor behind the bone, bone appears lighter on our radiograph. That difference between dark areas and light areas is contrast. And contrast is what allows us to actually see anatomy on an image. Without the differences in absorption, everything would look the same. The amount of photoelectric absorption depends on a few major factors as well. One factor is body part thickness. A thinner body part has less tissue for the X-ray beam to pass through, so less absorption takes place. A thicker body part has more tissue in the way, so there is a greater chance that photons will interact and be absorbed before they reach the image receptor. That is one reason thicker body parts require more exposure than thinner body parts. Another factor is the type of tissue. Different tissues absorb X-rays differently. Air absorbs very little. Soft tissue absorbs more than air, and bone absorbs more than soft tissue. And contrast materials like iodine and barium absorb even more because they have a much higher atomic number. This is why barium and iodine show up so brightly on X-ray images. They absorb a lot of the X-ray beam, which creates a strong difference between the contrast-filled structure and the surrounding tissue. It goes back to that atomic number, which is extremely important here. As the atomic number of the absorbing material increases, the probability of photoelectric absorption increases dramatically. In simple terms, higher atomic number materials are much more likely to absorb X-rays. That is why bone absorbs more than soft tissue. That is why iodine and barium are useful contrast agents. And that is why different tissues create different shades of gray on the final image. This chart here represents the effective number of materials that are important for us to know as radiologic technologists. Take the time to study and memorize them by writing out the type of substance and its effective atomic number out on an index card. Then do some math problems using the photoelectric formula. It'll definitely help you gain a better understanding and appreciation of the physics behind the photoelectric effect, and it may even win you a Nobel Prize. Okay, maybe it won't help you win a Nobel Prize, but it'll definitely help you on the registry and in your career as a radiologic technologist. Finally, beam energy also matters. As X-ray energy increases using high kVp, the X-ray beam becomes more penetrating. More photons pass through the patient without being absorbed, which means the proportion of photoelectric absorption goes down. Lower kVp, on the other hand, generally increases photoelectric absorption and increases image contrast. but it also increases absorption and therefore patient dose. So when the X-ray photon is completely absorbed by the patient and removes an inner shell electron, it increases patient dose because the energy is deposited in the patient. It does not increase occupational dose because it does not create scatter radiation, which we'll talk about next. And it also improves the image because it creates contrast between tissues like air, soft tissue, bone, iodine, and barium. That is why photoelectric absorption is both a radiation protection concern and one of the key reasons we can see anatomy clearly on an X-ray image. Okay, with that said, on to scatter radiation, and the first one we'll be looking at is Compton scatter, also known as the Compton effect. Now, Compton scatter is different from photoelectric absorption. With photoelectric absorption, the X-ray photon is completely absorbed and no scattered photon is created. But with Compton scatter, the X-ray photon is only partially absorbed. Here's what happens. An X-ray photon enters the patient's body and interacts with a loosely bound outer shell electron. The photon gives part of its energy to the electron and knocks it out of its orbit. That electron is now called a Compton electron. But unlike the photoelectric effect, the original photon does not disappear. Instead, the remaining energy leaves the atom as a scattered photon. So the simple way to remember Compton scatter is this: photon in, electron, and scattered photon out. That scattered photon now has less energy than the original photon, and it is traveling in a different direction, usually backwards towards the technologist. That is why we call it scatter. Now, let's talk about why this matters. Compton scatter affects three major things: patient dose, occupational dose, and image quality. First, Compton scatter increases patient dose. The reason it does is because ionization is taking place. An outer shell electron is removed from the atom, and that free electron can go to interact with the surrounding tissue. So even though the photon is not completely absorbed like it is in the photoelectric effect, energy is still being deposited into the patient. And on top of that, the scattered photon may continue traveling through the patient and may be absorbed later, adding even more dose. Second, Compton scatter increases occupational dose. This is one of the biggest reasons we care about it as radiologic technologists. During an exposure, the patient can actually become a source of scatter radiation. That scatter radiation can travel in different directions, including back toward the technologist or anyone else standing in the X-ray room. So when we talk about occupational dose, Compton scatter is the main interaction we are concerned about. This is why we wear lead aprons when needed. This is why we stand behind protective barriers. This is why we increase our distance from the source of scatter. And this is why we collimate properly. We are trying to reduce the amount of scatter being produced and reduce our exposure to it. Now, third, Compton scatter has a negative effect on image quality. It decreases image quality. Remember, the ideal image is created when some photons are absorbed by the patient and the other photons pass through the patient and reach the image receptor. That difference is what creates the light and dark areas on the image. But scattered photons do not carry useful anatomic information. They hit the image receptor from random directions and add unwanted exposure. This creates what we call fog or image noise. The result is an image with less contrast, more gray, and less visibility or fine detail. So photoelectric absorption helps create contrast, but Compton scatter reduces contrast. Now, what increases Compton scatter? The easiest rule to remember is this: more matter equals more scatter. If the body part is thicker, there's more tissue for the X-ray beam to interact with, so more Compton scatter can be produced. This is why larger patients or thicker body parts usually produce more scatter and low image contrast. Tissue density matters as well. The chest, for example, has a lot of air, so there is less tissue density and less scatter. The abdomen, on the other hand, is more dense. There is more tissue for the beam to pass through, so more scatter is produced. Now, field size also matters. When we open up our collimation and expose a large area, we are exposing more tissue. More tissue means more interactions, and more interactions means more scatter. When we collimate, we reduce the amount of tissue being irradiated, which reduces scatter and improves image contrast. Beam energy also plays a role. As KVP increases, the beam becomes more penetrating. Higher energy photons are more likely to pass through the body, but Compton scatter also becomes more important compared with photoelectric absorption. So as KVP increases, scatter becomes a bigger concern, especially because more scattered photons can reach the image receptor and reduce contrast. This is one reason that higher KVP techniques can result in lower contrast images. So the big takeaway is this: Compton scatter happens when an X-ray photon interacts with an outer shell electron, knocks that electron out of orbit, and then continues in a different direction as a scattered photon. It increases patient dose because ionization occurs. It increases occupational dose because scattered radiation can leave the patient and expose the technologist. And it reduces image quality because scatter adds unwanted exposure to the image receptor, which lowers contrast and creates image noise. So if photoelectric absorption is the interaction that helps create image contrast, Compton scatter is the interaction that fights against that. Lastly, in our discussion about photon interaction with matter, we'll be looking at coherent scatter, also known as classical scatter or Raleigh scatter. Now, coherent scatter is different from both photoelectric absorption and Compton scatter. With photoelectric absorption, the X-ray photon is completely absorbed. With Compton scatter, the X-ray photon is partially absorbed, an outer shell electron is removed, and a scattered photon is created. But with coherent scatter, there is no ionization. No electron is removed from the atom. Instead, the X-ray photon interacts with the entire atom. The energy of the photon is temporarily absorbed by the atom, and this causes the atom to become excited or to vibrate. And as a result, the atom releases that vibrating energy back out as a scattered photon. So the simple way to remember a coherent scatter is this: the scattered photon that leaves the atom has the same energy as the original X-ray photon, but it is traveling in a different direction. So the photon does not lose energy, it just changes direction. That is why coherent scatter is also called elastic scatter, because the energy is not changed. And it is also why it can still affect the image, because even though no energy is absorbed by the patient, a photon has still been redirected. Now let's talk about why this matters clinically. When we look at these interactions, we always want to think about those same three things: patient dose, occupational dose, and image quality. First, coherent scatter has no real effect on patient dose, and the reason is simple: there is no ionization occurring. No electron is knocked out of the orbit. No photoelectron or Compton electron is created, and no energy is permanently absorbed in the patient's tissue. The photon is temporarily absorbed and then released right back out as a scattered photon. So compared to photoelectric absorption and Compton scatter, coherent scatter is not a patient dose concern. Second, coherent scatter has essentially no effect on occupational dose. This is different from Compton scatter. With Compton scatter, the patient becomes the source of scatter radiation, and that scatter then can travel back toward the technologist or anyone else in the room, like we said earlier. But coherent scatter is usually forward scatter. In other words, the scattered photon usually continues in a direction closer to the image receptor rather than scattering backwards toward the technologist. So when we talk about occupational exposure, coherent scatter is not the interaction we are most concerned about. Compton scatter is the major concern for occupational dose. Third, coherent scatter can have a small negative effect on image quality. And the reason is because it still creates scatter. Even though the photon does not lose energy, it does change direction. And once a photon changes direction, it no longer carries useful anatomic information in the same way a properly transmitted photon would. If that scattered photon reaches the image receptor, it can add unwanted exposure to the image. That unwanted exposure can reduce contrast and make the image look more gray. But here's the good news. Coherent scatter is usually of little importance in diagnostic radiology. It is most likely to occur at very low photon energies, especially below the normal diagnostic range. So yes, coherent scatter can slightly reduce image contrast, but compared with Compton scatter, it is a much smaller issue. So the big takeaway is this. Coherent scatter happens when an X-ray photon interacts with the entire atom. The atom temporarily absorbs the photon energy and then releases it as a scattered photon with the same energy, but in a different direction. There is no ionization, there is no electron removed, there is no meaningful increase in patient dose, there's no meaningful increase in occupational dose, and the only real concern is a very small decrease in image contrast that's almost inconsequential. So if we put all three interactions together, photoelectric absorption is good for image contrast, but it increases patient dose. Compton scatter is bad for everything, really, the image, the patient, and for the technologist. And coherent scatter is mostly insignificant, but it can slightly reduce image contrast because it still produces scatter. That gives us the basic foundation for understanding how X-rays interact with matter and why these interactions matter so much in radiography. If you want to master the concepts you learned here today, take the free exam provided for you in the link below, teach what you learned here to someone else, and if you need help passing the ARRT registry exam, check out the 21-day registry review challenge at radtechregistry.com. Lastly, don't forget to share this lesson with someone you like, hit the subscribe and notification button, and speaking of like, don't forget to do the same for this video. As always, thanks for watching, and I'll see you in the next one.